I am Peter Wasif.
And we are doing the nitrogen generation systems.
So for our project, we wanted to start off and introduce our industry applications for nitrogen generation. So we're going to start off with food and beverage packaging, pharmaceuticals, chemical blanketing, electronic and soldering, heat treating, as well as our other engine uses in STEM, such as laboratory uses, laser cutting, power plants, printing, and tire inflation. For our economic side of nitrogen generation, as you can see here, our immense global industrial growth within nitrogen generating from 4.2 billion US dollars in 2021 increased exponentially to 5.5 billion US dollars in projected to grow like that in 2026. And as well as the growth rate in the market, we can also appreciate the growth in the population, urbanization, and demand now for nitrogen generation products. In our various industries, for example, food and beverage, or any of the others listed in the previous slide. And through our production processes for nitrogen generation, we have cryogenic fractional distillation, adsorption, and membrane separation, which we will expand on, as well as a common industry standard of a 95 to 99.5% purity.
So the first production process is cryogenic fractional distillation, which uses compressed air from the environment. It is put through a water and carbon dioxide removal system, through a heat exchanger to actually cool the air intake, which I will expand on in a little bit, which is then put into a distillation column to remove the nitrogen from the oxygen, which is all that should be left in the gas system. The reason that we need the heat exchanger to cool the air intake is that the operating range is between negative 190 and negative 180 degrees Celsius, which is between the boiling points of oxygen and nitrogen, allowing nitrogen to remain in the vapor phase and oxygen to condense into a liquid. The potential concerns with this, however, is a poorly insulated distillation column, the air compressor sizing, our heat exchanger cooling the system enough, valve leaks, so a waste of our air, a waste buildup in the water removal columns, the cavitation, if liquid, oxygen, or water make it through the systems, we could have cavitation in our pipes and distillation column, and it is a pressurized system, so that is a safety concern.
For our adsorption, we have PSA nitrogen generating or pressure swing absorption technology that we use through two towers, which are both filled with CMS or a sieve, where we take compressed air throughout the bottom of one of the towers, which is whichever one is currently doing the compressing, and then it pushes out oxygen on the other side. No, it pushes out nitrogen on the other side while separating it from the oxygen. So oxygen, nitrogen in, and then nitrogen out. Is perfectly absorbed by the sieve inside of the columns, allowing it to pass through and allowing that when one is full or can no longer compress, it switches onto the other online tower, so that they just go back and forth and that's it. So with the adsorption of the oxygen is a two-stage system. The adsorption plus the depressurization. As you can see in the image, We have the process that happens within the columns where the oxygen and the air and the nitrogen and oxygen pass through the material and then push the nitrogen gas out. Um, with this system, a great benefit of it is you can pretty much run these 24/7 with as long as you keep uh, decent maintenance on a pretty regularly scheduled basis. These can run up to a decade or more, uh, as well as they're very low cost in ownership, and you can pretty much use adsorption in various parts of the industry and scale it to your liking and get a, a good amount of it. With potential concerns, we have air compressor size, which you must take into account. Safety valves, make sure that those are working properly. So phase switch timing, and effective depressurization. If you can't effectively pressurize, you will not get a good purity of the nitrogen gas.
And the final separation is a membrane separation, which takes compressed air, puts it through an electric heater, which it promotes diffusion, while air, water, and carbon dioxide diffuse through the membrane. Nitrogen does not. These membranes are called hollow fiber membranes. They are usually something like cellulose acetate or polysulfone, and the nitrogen that comes out is obviously sent to our customers. While fairly simple in application when you know what membrane to use, the actual theory behind it can be quite complex. It's using the Maxwell-Stefan equation, which has terms for the concentration diffusion, a pressure diffusion, a forced diffusion, and a thermal diffusion term, which all of these terms would be applied to each gas separately and together through this selectively permeable membrane, which does not allow nitrogen to diffuse through it. The potential concerns with this, however, is if the membrane becomes worn or the pore size increases in the membrane too much, nitrogen can begin to diffuse through it. The air compressor sizing, making sure that we do not have too much air or too little air being pushed through the system at any given time. Having the electric heater sized properly to heat the air to the temperature we need it to promote diffusion. And again, the safety concern is a pressurized system can have issues if it depressurizes too quickly. Now, selecting the process. Picking between the three, the fractional distillation, the adsorption, and the membrane separation. First off, we look at the purity. All three of these have fairly high purity. Fractional distillation can produce the largest quantity at a consistent purity. It is the most commonly used in industry. However, it is more expensive, has a higher amount of maintenance, and is very, very sensitive to temperature. Adsorption, again, has high purity, can produce 24/7, is a low cost. It can be easily interchanged between different uses for the nitrogen. They're durable, they have easy maintenance. However, they can't produce as much nitrogen as the fractional distillation without eventually being less cost effective. The membrane separation also is high purity. It has a lower production rate of nitrogen just due to the nature of its separation. However, it is a very low cost, can also produce constantly. The membranes are fairly durable, so they're easy to maintain, and it is easy to scale. However, again, with the membrane separation, as you try to produce more, it becomes less cost effective. So really selecting the process comes down to the needs of your process. If you need a lot of nitrogen, you would go with the fractional distillation. If you don't need very much, you could do a membrane separation. And if it's somewhere in the middle, adsorption is usually the best option. These are our sources. And that is all.